Hello everyone, how are you doing? If you have any question from the previous session, just ask me your questions. Otherwise, we will start the third session today. Just let me know if you hear my voice very well.
Yes, it's fine.
Thanks, Vincent. So today we are going to start by solving equation 2.40 and 2.57 in order to finish chapter 2, and then we will go for chapter 3 today, force vibration. So let's start off with problem 2.40. So I will try to write very small in order to have a big picture to what we have. And uh, 240, it says a vibrating system has the following constant, a mass. So let me write the problem at first. 0.40. When it says a vibrating problem, you can simply draw a mass spring damper system like this, okay, for any vibrating system. Mass spring damper, okay, KCM. So M is given, basically M is given 70.5 kilogram, and a stiffness is given 70 Newton per centimeter, and the damping coefficient is 0.70 Newton per centimeter per second. So we are supposed to determine a damping factor, or theta, right? Damping factor, the natural frequency of damp oscillation. The natural frequency of damp oscillation, omega d. C, you are supposed to determine logarithmic decrement, so-called delta, logarithmic decrement. And D, ratio of any two consecutive amplitude. For example, x1 over x2 or x2 over x3. So A, damping factor, omega d, damp natural frequency, delta is so-called logarithmic decrement, and D is basically ratio of any two consecutive amplitude. So at first, if you take a look at here, the stiffness and damping coefficient is not represented by a SI unit. So you have to change it by Newton per minute. So you have to at first multiply by centimeter over meter. Each meter is correspond to 100 centimeter, right? So therefore, it is equal to 7,000 Newton per meter, right? And also you have to correct it multiplied by centimeter. Each meter is 100 centimeter, therefore it is equal to, so it is equal to 70 Newton per meter per centimeter, or simply 70 Newton second per meter. So at first you have to create SI unit. So damping factor is very easy. Damping factor is nothing but C over C critical, right? C is the damping, and the damping constant basically C is given, and C critical is 2m omega n, or you could use other form of this formula, which can be represented by 2 square root of k multiplied by m. The reason I use the second relation is that we have easily k available and m available, therefore we could easily find critical damping. So the zeta is equal to C is given 70 and K also is given, M also is given, right? You could easily calculate the damping ratio. So which is equal to 0.1. 0.1 is damping ratio, or in some references they put 10% damping, correspond to 10% damping. So we are done with first part A, and B, we have to basically calculate the damp natural frequency. Damp natural frequency is omega n natural frequency multiply 1 minus zeta squared. Omega n itself is square root of k over m. We already obtained k. We are given k 7,000 Newton per meter divided by mass, which is given 17.50. Therefore, omega n is can be obtained as omega n. So if I multiply by, so I have the final answer for the, okay, the 7 over, so 20 radian per second. Therefore, the damp natural frequency can be obtained as 19 radian per second, or 1 minus squared, approximately, yes, approximately 819. So $89, so radian per second, 19.9 radian per second. There is a small difference between the two damp natural frequency omega d and natural frequency due to the damping ratio. So we are done with basically part B, and we will go for part C, logarithmic decrement. And for when we have such a system, vibrating system M, if we disturb and if we basically move a system due to the initial condition, the response of the free vibration would be something like this, right? Since free vibration after some time due to the available damping, the response x of t gradually decrease and approach zero, right? Time. So if we plot a tangent curve or so-called push curve, there is a e to the minus delta t, the delta so-called logarithmic decrement. So, which is very important, and usually you will be asked in the midterm to calculate this logarithmic decrement. It's very important question. So there is a very simple formula in the textbook. You could refer to it in order to calculate the logarithmic decrement delta, which is equal to 2 pi zeta divided by square root of 1 minus zeta squared. So since we have zeta, delta can be easily calculated. 2 pi multiplied by 0.1 divided by 1 square root of 1 minus zeta squared. Therefore, logarithmic decrement delta would be 0.6312. That's it. So it will give us a geometrical interpretation of how response will be decayed. If delta is very high, the response of the system dramatically decrease, right? You could have some vision how the system will behave, and the response of the system, how they gradually become zero. A geometrical tools for interpretation of the response of the system. So next part and the last part is ratio of any two consecutive amplitude. Amplitude is maximum displacement. Maximum displacement. If I go to figure, this is amplitude. X1, X2, X3, right? And then so ratio of any part D, ratio of to any consecutive amplitude such as X1 over X2 or X2 over X3, it is equal to, if you go through the textbook, it is equal to e to the power logarithmic decrement. And logarithmic decrement is obtained in the previous part as 0.6312. Therefore, this ratio is 1.88. So this is typical question in the chapter 2, which we were supposed to find damping ratio, logarithmic decrement, and damp natural frequency. So if you have any question, you can ask me. Basically, this logarithmic decrement and just says that what is the rate of decay of free vibration or free oscillation. So just a small note, and we are done with first question, and then we will go for question 2.57. So there is a two rigid uniform bar which is attached by using spring, torsional spring, and this also attached to a mass M, which is attached to the spring with a stiffness of K. So torsional spring, uniform bar L. So the system shown in this figure has two rigid uniform beams of length L and mass per unit length M, hinge and the middle and resting on rollers at the test stand. The hinge is restrained from rotation by a torsional spring K and supports a mass M held up by another spring K to a position where the bars are horizontal. It means right now they are in a static equilibrium position. Determine the equation of motion using virtual work. Virtual work is another technique similar to the Newton's second of law and Euler formula to derive equation of motion. When we say, and in second Newton of law, basically we say the Newton approach, we normally say summation of forces is mx double dot, and summation of momentum is equal to the around point O J naught theta double dot. So there is a D'Alembert rule that we could take a look at a dynamic, we could consider a dynamic problem as a static problem if we apply a imaginary inertia. So summation of forces minus mx double dot is equal to 0, a static problem, right? Summation of m minus j naught theta double dot is equal to 0. It's D'Alembert law, which are equivalent formula. So by taking advantage of D'Alembert law, we could develop the principle of virtual work. And if I want to give you a hint for principle of virtual work, and so basically virtual work is suitable for is more suitable for system of interconnected bodies of higher degree of freedom system, and is defined virtual work typically is defined the work done by a real force acting through a virtual displacement so it means that we apply a very infinitesimal, a small oscillation, a small movement, and then we calculate total work done by all the forces, and summation of this work should be 0. Why? Because the virtual displacement is very small. So summation of all work done by each force, delta is equal to 0. This is the principle of virtual work, the virtual displacement. Very small displacement, virtual displacement. So all you have to do is just calculate the forces that opposes the motion. As soon as you apply any virtual and very small displacement, you have to see what are those forces that oppose the motion, and then calculate the corresponding work by these forces and make summation of those and equal to the 0, and then you will indirectly and automatically come up with the equation of motion. So work is also equal to force multiplied by displacement, right? Displacement can be written in a torsional case r theta, right? So therefore it can be written by F multiplied by R by theta. F multiplied by R is momentum, right? Therefore, it can be written by M theta. So therefore, work can be calculated as force multiplied by displacement, or momentum multiplied by theta rotation. And so another definition of virtual work, it says that if a particle or a rigid body is in an equilibrium position under the action of number of forces, the total work done by the forces for a very small arbitrary displacement is 0, which is, we write here, total work should be 0, right? The principle of virtual work. The principle of virtual work make it possible to find the conditions of equilibrium of a system without introducing unknown constraint forces, which significantly simplify the solution. So let's start and to derive the virtual work. Before we proceed further, I want to compare the Newton law and principle of virtual work. Typically in Newton law, you have to plot free body diagram, but in virtual work, it is not necessary, no need for free body diagram generally, but in the exam, try to always draw free body diagram for each problem. It just gives you a good it's a good tool to come up with the right answer. And generally, the Newton law is vector quantity is a vector quantities. On the other hand, virtual work is a scalar quantity. So that's it. So let's start just a quick comparison. So in order to apply the principle of virtual work, we move a system a little, we give a system a small displacement. So if I displace the lower mass toward down a little bit, so I have the mass, so I displace a mass toward down, therefore the lower spring at first opposes the motion, right, kx, the spring force, and there is a torsional spring kt theta from both sides, kt theta, because the kt is attached between the two beams, you have to write 2 kt. And now we have to apply the D'Alembert law and also consider the inertial forces, because in virtual work, we suppose the system is in a static position. We apply a very tiny movement. So we basically facing with a static system, right? So we apply the inertial forces, mx double dot, and to inertia for these two beams. For a beams, consider, in order to calculate the corresponding inertia, we have a beam attached from one end. So if I call the middle point C and this point O, and suppose this is L over 2 and this length is L over 2 and total length is L, the mass moment of inertia around point O, according to the parallel theorem, is equal to mass moment of inertia around point C plus OC squared. Therefore, I around O would be equal to 1 over 12 m L squared plus m multiplied by m L over 2 squared, which is equal to 1 over 3 finally m L squared. This the corresponding inertia for each beams which oppose the motion, 1/2, 1/3 m L squared and 1/3 m L squared. So all you have to do, we recognize all the forces that opposes the motion by applying a tiny displacement. So now we have to calculate the corresponding work done by each forces, right? So there is a small virtual displacement, and also there is a small virtual rotation, delta theta, right? Which are correspond to each other. So now we basically, by taking a look at to this figure, we try to write the work done by each force. So summation of all virtual work should be 0. Therefore, there is a inertial force if we consider positive direction. Lower direction is our positive direction, Therefore, the inertial force is toward up. We write minus mx double dot, which is a force, right? Which is a force multiplied by corresponding virtual displacement, as well as there is a spring force minus kx. So this is basically virtual displacement, and this is virtual work. Similarly, other terms, the stiffness, the spring force in the lower stiffness is kx, right? Kx multiplied by virtual displacement. And also, we have two torsional spring here. And you have to calculate the corresponding force minus 2 kt torsional springs multiplied by theta. It will give you the torque basically, and torque multiplied by virtual rotation will give you work, as I proved in the upper part. So at the end, we have just two inertial forces. We will add them, which oppose the motion, 2ml squared over 3 multiplied by theta double dot divided by virtual rotation theta. So this is momentum, this is or torque, this is virtual, the rotation, and this is work. So the principle of virtual work is saying that if you apply a very, very small movement, very, very small or virtual displacement, the total work should be 0 because the delta theta is very, very small. So you make it equal to 0. And then by canceling out delta theta and delta x from both sides, because we could relate the delta x as L multiplied by delta theta, because x is L multiplied by theta, right? There is L and there is a theta, there is a x. When x very small, we could say, we could take variation from both sides. Therefore, we have variation of x is equal to delta multiplied by variation of delta theta virtual. So here, if you just plug in any delta x as L multiplied by delta theta, and then try to removing and canceling out delta theta from both sides of this equation, at the end you will come up with this equation of motion by simplifying the above equation, basically removing delta theta. Just divide both sides, right hand side and left hand side, divide by delta theta, and then you will reach to this equation at the end, m L squared plus 2/3 m L squared multiplied by theta double dot plus k L squared plus 2k multiplied by theta is equal to 0. This is the final equation of motion using principle of virtual work. Equation of motion. So you could call this term as effective mass or effective stiffness, equivalent mass, and this is equivalent or effective stiffness. So effective mass theta double dot plus effective stiffness theta is equal to 0. This is how we basically obtain equation of motion using principle of virtual work. Normally, if you are not asked a specific approach and method to derive equation of motion, so far it is so easier to take advantage of using second Newton of law and Euler formula. Otherwise, you're asked to just use this principle of virtual work. And for the final term, you will be always asked to derive equation of motion using Lagrange approach, which is a very simple approach. You will learn how to do that. And so just let me know if you have any question. I will try to explain it to you another time. Basically, we are done with chapter 2, the free vibration, and chapter 2 is concerned with force vibration. So chapter 3, force vibration. And let's start off with the first problem, which is 3.2. 3.1 and 3.2, which are connected to each other. So anybody knows what is the main difference between the force vibration and the free vibration? As I said in the first session, the principal difference between the free vibration and force vibration is that when you have a mass spring damper system and apply a initial condition, it will start oscillate, and then the amplitude will be 0 at the end. So the frequency of the free vibration is the natural frequency of the system. However, in the forced vibration, the frequency that the system will vibrate is exactly the same as what we apply externally. So if we apply a force F naught sine of omega naught t, the frequency of force vibration is equal to omega naught. So if omega naught is 10, the frequency that the system will vibrate is 10. If omega naught is 100, the frequency that the M is under or subjected to is omega naught. However, for free vibration, the frequency that the system vibrate is always natural frequency. This is very important. This is a summary of chapter 2 and chapter 3 in one shot. So, and therefore you have to connect somehow they could connect omega to tau period of the vibration, right? So let's start off the problem 3.1 and 3.2. A machine part of mass 1.95 kilogram vibrates in a viscous medium. It means it is subjected to damping. There's a damping in our system when it says it's vibrate in a viscous medium. Viscous medium, it means that C is not 0. We have damping. We have damping in our system. So a machine part of mass 1.95 kilogram vibrates in a viscous medium. Determine the damping coefficient. Damping coefficient, C. Determine the damping coefficient when a harmonic exciting force, exciting force is always can be represented by F of t equal to F naught sine of or cosine of omega t, right? So harmonic exciting force of 2446 Newton. It means this is F naught, the amplitude of force. Results in a resonant amplitude of 1.27 centimeter with a period of 0.20 seconds. So basically we have to calculate damping coefficient when this system is subjected to a harmonic force of 24 Newton, which results in a resonant amplitude of 1.27. So the resonance occurs when the excitation force is equal to natural frequency of the system. In this case, the amplitude of vibration is gradually increasing and increasing. In case of damping, only tools that can reduce amplitude of vibration is damping. Very important. In case of resonance, our tool is only damping. In this case, when at resonance, we basically need damping in our system. Of course, we use damping in other cases, but at resonance specifically, our only tools is, so always we have to consider some percentage of damping in our system in case of resonance, because we don't know when we design a mechanical system, we don't know about, for example, when you are designing a bridge, we don't know about the main frequency of wind that will come and occur to the building, to the bridge, and also in case of airplane, everything. So when you design a mechanical system, you always have to have a damping. Otherwise, in case of resonance, you cannot control the amplitude of vibration. So the response of a forced vibration basically is a steady state response, particular response, usually represented by x summation of x sine of omega t plus phi, right? Or minus phi. There is a phase lag, basically. And capital X is our amplitude. Amplitude is can be obtained by F naught over K over K minus M omega S squared plus C omega S squared, or it can be written as F naught over K S square root of 1 minus R S squared plus 2 zeta R. Generally, in the exam, you will be given some formula, but it is better to read how this formula will be. It can be derived, and in case if you are not given any formula, you could easily, you have to solve how we could reach to this formula by solving the equation of motion, right? mx double dot plus cx dot plus kx is equal to 0, and then f of t, you could easily find if you consider a general force f of t as f naught e to the I omega t, and response would be something like x e to the I omega t minus phi. So you could easily derive this amplitude by solving this equation, in case you will not have any formula sheet in the exam, but definitely you will be given. But try to solve this equation of motion. In case you don't have any equation, you can at least you can obtain the equation. So if you take a look at here, we have the amplitude, right? There's x is equal to is amplitude of vibration f naught divided by k divided s squared of k minus m omega s squared plus c omega s squared. So you could easily find the amplitude. In case of resonance, amplitude is given in case of resonance. So X resonance is given as 1.27 centimeter. Resonance when is omega n. We are looking for C. So if I write again the equation, X is F naught divided by S square root K minus M omega S squared plus C omega S squared. So in case of resonance Then m is equal to omega n, therefore this is going to be 0. Why? Because k is m omega n squared. When omega is omega n, k is equal to m omega n squared would be equal to m omega squared. Therefore, the first term would be 0. X of resonance, therefore, is equal to f naught over c over omega. You could easily calculate the damping coefficient, the damping constant, damping coefficient by solving this equation for c. C is f naught over x of resonance multiplied by omega. So f naught is given to us. Basically, f naught is nothing but 24.46 Newton multiplied by, divided by x of resonance 1.27, which is centimeter. You have to change it into SI unit. You have to multiply by 10 to the minus 2 and then multiply by omega. So omega is not given to us. What we can do basically here is you could say that omega is 2 pi over tau. Tau is the period of oscillation, is given to us. So therefore C would be, or if I want to write it parametric, I could say f naught over x of resonance, omega is 2 pi over tau, which is equal to f naught tau x of resonance 2 pi, right? So because we don't have omega basically in this problem specifically, we have to somehow calculate the C. So here we don't have omega, we replace omega by 2 pi over tau. Therefore, the damping constant can be easily obtained by this equation. F naught 24.46, tau is given 0.20 second. X resonance is given 1.27. You have to change the SI unit by meter and multiply by 2 pi. Therefore, C is obtained as 61.3 Newton second per meter. This is how we obtain the damping constant following equations 3.1. 3.2 is just referred to question 3.1, and it says that basically if the system of the problem 3.1 is excited by a harmonic force of frequency 4 cycles per second. In this case, we have only the excitation problem, excitation frequency of 4 cycles per second. So it is not good to show it with omega because cycle per second is nothing but frequency, right? Hertz, frequency in hertz. So it is better to say F is 4 cycles per second or 4 hertz. I want to repeat the questions. 3.2, we are done basically with the first question. 3.1, we were supposed to calculate the damping coefficient C in case of a resonance. But in question 3.2, it says if the system of question 3.1 is subjected by a harmonic force frequency of 4 cycles per second, what will be the percentage increase? What will be the percentage increase in the amplitude of force vibration when dashpot is removed, when C is dashpot or damper is removed. We want to see how much amplitude of vibration will increase if we don't have damping. In case of resonance, if we don't have damping, the amplitude will be dramatically increased. We want to see that. So we have to calculate the increment in the amplitude of force vibration in two cases, with damping and without damping. So we have the formula is very easy. X amplitude of force vibration, F naught over K, K minus M omega squared plus C omega squared. Or you could use the dimensionless, which is better formula. Dimensionless formula is equal to F naught over K 1 minus R squared plus 2 zeta R squared. I made a mistake, sorry, here. I shouldn't have written K for this formula. These are the same, but this is the suitable format. It's more, it's depending on you. You could either use the left or the right one. The right one is dimensionless formula. R is the frequency ratio, omega over omega n. So here, in the first problem, is correct. I wrote it correct. Okay, here I made a mistake. So all you have to do is just writing this ratio, amplitude of vibration in case of undamped system, undamped, without any dashpot, over amplitude of vibration when we have a damper in our system. If you divided 2 times this formula, you will reach to this equation. One minus R squared plus 2 zeta R squared divided by 1 minus R squared undamp over damp. So if you divide it 2 times, in one case we don't have in the undamped case we don't have zeta. For undamped case you have to just put zeta equal to 0. But for a damped case zeta is not equal to 0. If you divided the two formula together, you will reach to this equation, and you have to basically just plug in R and zeta. If I have R and omega and zeta, therefore I could find X undamp over X damp. So in order to calculate this ratio, all you have to do is just calculating the R and zeta. R is nothing but damping ratio, which is omega over omega n. Basically, which is equal to 2 pi f or 2 pi fn. F is given to us 4 cycles per second, and the natural frequency is given to us from the previous question. It will be equal to basically omega. We had the omega in the previous question. Because we had a tau, you could easily find the omega. Because omega n is 2 pi tau. When you have a tau, you could easily find, in the previous problem, omega was omega n, right? The previous problem. So omega n from the previous problem is obtained as 3140, problem 3.1, because we are talking about the problem. So this is the ratio. 2 pi. So R is finally 0.8. So we are done with basically R. If I have zeta, so R is okay. If I have the zeta, I can calculate the ratio. Zeta is C over C critical, basically. In the first problem, again, I obtained C as 61.3, problem 3.1. So I have a C, and C critical is 2m omega n, 2m omega n, and which is equal to, m is given in the first problem, 1.95 kilogram. Omega n we calculated is 3141 radian per second. Therefore, damping ratio is half. So we have damping ratio, we have basically R. You could easily calculate this ratio. You were supposed to know. So you have R, you have zeta. Therefore, easily this ratio can be obtained as as 1 minus 0.8 squared plus 2 zeta R squared divided by 1 minus R squared, which is equal to 2.44. So if I want to calculate the percentage is change over initial value multiplied by 100. Percentage increase, right? So we have X undamp over X damp as 2.44. We could give a denominator 1. So the change, therefore change is I mean, the change is 1. From 1, we reach to 2.44. So the percentage increase is second case minus the first case divided by initial multiplied by 100, which is 144% increase in the amplitude of vibration if we don't have a damper in our system in case of resonance, which is very dangerous. It's very huge. 144% increase in the amplitude of vibration if we don't have any dashpot in our system. So just let me know if you have any question. Otherwise, we will go for next problem. The next problem is 3.7. 3.7. This is very important. In one semester, it was a question in the midterm or final, I'm not sure. But I know that this is one of the questions in the midterm or final. It's very important. Try to do that. Try to solve it as much as you can. So 3.7, very important, my friend. So let me draw the problem. There is a mass spring system M, which is attached to a dashpot C to the wall, and from right-hand side attached to a spring. So the right-hand side of this spring can be moved, can be displaced by x2, x2. So suppose that the movement of the mass is represented by x1. If we applied a force displacement amplitude, a force, if we just move the right hand side of the spring by x2 sine of omega t. So what would be the equation of motion? Let me read the problem for you. So for this system shown in this figure, set up the equation of motion and solve for the steady state amplitude and phase angle using complex algebra. So we have to basically derive equation of motion and then solve for amplitude and phase using complex algebra. So the first step is deriving equation of motion. So for any linear system like this, you could easily and simply take advantage of second Newton's law. If I draw the free body diagram of this equation, 3.7, 3.4, we missed 3. We will come back for 3.4. We missed 3. We will come back for 3.4. And so equation of motion easily and simply just using the second Newton of law. So if I displace the mass to the right side, I consider a positive direction. That's why I displace the system to the right. If I displace the system to the right, the left spring simply opposes the motion. The left damper simply opposes the motion as Cx dot 1, and also the right spring also opposes the motion. However, the spring force is K multiply. If you take a look at here, you will see that the spring is from left hand side is connected to x1, and from right hand side is connected to the x2. So you have to consider a relative deformation in order to find the final deformation applied to the spring. So the spring force would be K multiply the relative displacement. You have to start from the mass we are working on, x1 minus x2. So not x2 minus x1, right? x1 minus, why? Because we are trying to derive equation of motion for x1. So this is free body diagram. Always try to plot free body diagram. In case in one person you have not come up with the right final answer, the marker will give you partial mark. Your professor will give you partial mark if you draw the free body diagram. It's very important. So, and then you could easily apply the second Newton of law. Summation of forces applied to this mass is mx double dot, right? So minus cx dot 1, because right hand side is our positive direction, and minus k x1 minus x2 is equal to mx double dot. We are focusing on x1 basically. It means x1, right? Summation of forces applied to the mass 1 is equal to m1 mx double dot 1. If I further simplify this equation, I will come up with this equation as mx double dot 1 plus kx dot cx dot something cx dot 1 plus kx1 is equal to kx2. So which x2 is given as x2 sine of omega t. This is the equation of motion. We are done with first part, equation of motion. So we are asked basically to solve the equation of motion, right? Simply you could, from right hand side, x2 is given as x sine omega t. However, for the sake of simplicity, by taking advantage of complex algebra, there is a simpler way of solving this equation. Rather using x sine of omega t, you could use basically a general format for harmonic oscillation. You could say that, you could rather say x2 in general case is x e to the I omega t. General complex algebra, because e to the I theta is equal to cosine theta plus I sine theta, right? So it's more general and more easier. Therefore, for solving this equation, let me take advantage of this equation, and we know that the response of force oscillation is nothing but x1 is x sine of omega t minus phi. There is a phase lag between output, which is x1, and input x2. Why? Because we have a damping in our system. If we don't have any damping, the phase would be zero. Similarly, for the sake of simplicity, by taking advantage of complex algebra, we will use this equation, rather x of t is x e to the I omega t minus phi, complex algebra. So let me focus in these two. For solving this equation of motion, let me call this equation 2, equation 3, sorry, and let me call this equation 2, and let me call this equation 1. So by plugging 2 and 3,
Sorry, Hossein, I can't hear you. Okay, I think I hear you now.
Okay, there was a problem. I didn't know what happened. So I was trying to mention the problem 3.7 is one of the midterm problem in the previous semester. There is a system M from left hand side attached to the damper, from right hand side attached to the spring, but the right hand side is subject to harmonic oscillation x2. Okay. At first step, we are asked to derive equation of motion, and as the second step, we need to solve the equation of motion using complex algebra, and we are supposed to, and we are asked basically to calculate corresponding phase and magnitude x and phi. As I told you, for deriving equation of motion, we could take advantage of second Newton of law because we are facing a linear mass spring system. I consider positive direction toward right. That's why I displaced the system toward the right a little bit. And then I calculated that the forces oppose the motion, like Cx dot 1 damper force and K multiply x1 minus x2. And then I construct the equation of motion like this, okay? For the sake of simplicity, by complex algebra allow us to simply solve the equation of motion. Rather, consider x2 as x sine of omega t. We could generally consider x2 is x e to the I omega t, right? And then the response of a steady state forced vibration steady state system is nothing but x1 x sine of omega t minus phi. Phi is the phase lag between input and output when and only when we have a damping in our system. If we don't have a damping, phi will be 0. So for the sake of simplicity, we wrote x1 of t is capital X e to the I omega t minus phi. So we could easily plug in here x1, x dot 1, and x double dot 1, and then solve for x. We took derivative in order to find x dot and x dot double dot 1, and then plug in all the term here, the equation of motion. So by factor out e to the I omega t and e to the minus I phi, and by removing e to the I omega t from both hand side, we have come up with this equation. From left hand side, we obtain x1 e to the minus I phi, and from right hand side, we obtain kx2 divided by k minus m omega squared plus I omega c. I call numerator as z1, and I call denominator as z2. I want to treat numerator and denominator as a complex number. For a complex number, we know that magnitude of Z1 over Z2 is nothing but magnitude of numerator divided by magnitude of denominator. And for the phase of a fractional complex number, phi of Z1 over Z2 is phi of numerator minus phi of denominator. We have these two formula, and then we could apply to find the corresponding phase and magnitude from right-hand side of this equation, from which we could then find the phase and magnitude of 1. If I call them F1 is much more easier and simpler. F1 x1, okay? So we know that for any complex number, basically, if any complex number is a plus minus ib, the magnitude is a square root of a squared plus b squared, and phi is tangent inverse of b over a. So right hand side Z1 over Z2, and then I applied phase and magnitude. Magnitude is kx2 over s square root of k minus m omega squared plus c omega squared. This is magnitude of the right hand side, and the phase of right hand side is phase of numerator minus phase of denominator. Phase of numerator is 0, phase of denominator is tangent inverse of minus c omega over k minus omega squared, right? So from left hand side, I had x1 minus e to the minus I phi 1, and from right hand side, there was a fractional, which I found magnitude m and corresponding capital phi. Therefore, by taking looking of the left and right hand side, we could say that x1 is x and phi is capital phi. And this is how we obtain basically the magnitude and phi. Phi is here. This is phi, and which is equal to phi 1. And this is the magnitude. So Vincent, if just let me know if you have any question. It's very important question. Try to do it by your own one time. 3.7. I missed question 3.4. Next session I will take care of this problem. So 3.4, we are done with 3.1, 3.2, and 3.7.
I have a question.
Yes.
If we go back from the beginning of the problem.
Sure.
Why we use the x1 minus x2 instead of x2 minus x1?
A very good question, Vincent. Very good question. In order to not forget and in order to not make a mistake, what my method is that I usually, at first step, I consider a positive direction. Okay, I will tell you why. At first step, if you do that, you will never make a mistake. Okay, just consider a positive direction, right hand side. Okay, and then in order to plot free body diagram and then deriving equation of motion, just move and displace a little bit the system in the direction of positive direction we assume. So we considered right is positive. So I move system to the right. Okay, these two spring force and damping force oppose the motion. So damping force is to the left, but the spring force, if you take a look at here, you will see that the right spring is attached between the 2 points. From left point, there is a x1 and from right point there is a x2. Both left and right end of this spring is subject to the movement. It is not a stationary, neither x1 nor x2. You have to, in this case, take advantage of a relative displacement in order to find the final deformation, as if the k is between such this system. For example, k1 m1, right? In the next chapter we will take care of multiple degree of freedom system, k2 m2 attached to the m3 k1 k3 m3. So we apply a displacement. So for deriving equation of motion, for we could apply second Newton's law for each mass. Only this mass just has from the left end is constant, but this spring and this spring has relative displacement. You have to consider a relative displacement, and since we are, this is the point you ask, since we are writing the equation of motion for x1 m1, basically we always start from the mass we are working on, m1. If you are writing, if you were supposed to write equation of motion for m2, you will write x2 minus x1. Since I'm trying to derive equation of motion for m1, I always write x1 minus x2, rather x2 minus x1. So you have to always follow this rule, and you will not always, you will never make mistake. So because we are basically try to derive equation of motion for m1, and we displace m, and we always write x1 minus x2.
Okay, thank you.
You're welcome. So I will send you the movie and the file. So try to solve some problems, and you could solve 3.8, which is similar to 3.7, or also you could try to solve some problems in order to make sure you will master of this deriving equation of motion, either using complex algebra or the Newton law. Is very important. So if you have any question, you can ask. Otherwise,
since we have a little bit of time,
right?
Can we go back to 2.57?
2.57. Yes,
yeah.
the virtual work. Okay. The first question basically we saw, I think, 2.
Yeah. I'm a bit confused about this problem for the virtual work.
Okay. For the.
So how you find the I? Is this gonna be given in the exam, these formulas, or you have to derive it like you did?
I think normally you will be given most of the formula, but it is better to somehow memorize and to write down, and I think you will be given but this equation will not given. Basically, this is a theory, and I of O is IC, like the last session we solved similar problem, MD squared. So you have to better somehow memorize this parallel axis theorem. I around point O is equal to I in prime center of gravity plus D, which is the difference between these 2 points, O and C is D. And because the two beams attached to the left and right point, we must to calculate mass moment of inertia around point O, rather around point C. And for your specific question, for example, I see maybe this equation will be given 1/12. this is another formula we use. But this one you have to know. But you may ask your professor whether he's going to give you the formula for mass moment of inertia for a beam, for a disk. Normally it should be given to you, but it is better to ask your professor. Specifically try to ask you will be given or not the mass moment of inertia formula for different shape beams, disk.
Okay, thanks.
You're welcome. So you have any other question?
No question.
Okay, take care and see you next week, Monday. We will continue chapter 3.
Yes, see you.
See you. Thank you.